Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture number 7 of this series. So, in this lecture I will discuss about the surface and different surface dependent engineering properties. So, surface plays a very important role in determining many important properties of matter, and it is nothing but may be defined as the interface between two phases or two grains in the same phase. Surface is very important because it is the region of highest energy, it faces the environment, and this is the part of the component where stresses are often highest. And as a result of which you will find that on the surface there are many important phenomena and also many important degradations also they initiate from the surface. So, unless and until we understand the surface, it is very important to design the surface of any component for having the tailor-made in its properties. So, if you talk about the surface, then first thing which comes into mind is nothing but surface energy. Surface energy is nothing but the extra energy which is required to create the surface. So, it is actually represented in terms of specific surface energy. This is the excess energy per unit surface area. So, the unit is joules per meter square of surface. Now, it is basically nothing but it depends on the interface actually. So, you can understand that surface may be that what are the surface energy or interfacial energy, it is very much dependent on the environment. Whenever you talk about the surface and interfacial energy between solid and liquid, it is having some energy value. On the other hand, if you talk about the interfacial energy between solid and gaseous species, it is having some energy value. On the other hand, when you talk about the different planes on the surface, it is having different energy values. So, it is required, it is very much dependent on the environment and also many other parameters on the surface, particularly at which plane the surface is created. And it is nothing but because of the fact that when you create the surface, we need to break certain number of bonds from the surface to create the interface, and as a result of which surface energies we need to spend some energy to create the surface. So, for example, this is the case for solid to liquid interface. If it is FCC metals, then naturally it is having the, and if you create the surface along 1 plane, then it is having the coordination number of 9, and if you would like to create the that solid gas interface, then naturally you have to break 3 numbers of bonds to create the surface between the solid and gaseous species. So, depending on the number of bonds which you are breaking, the surface energy also varies. Now, if you talk about the role of surface energy or its implications or importance, you will find that it influences many important phenomena, like for example, if you talk about size and shape of the droplets, then atomic arrangement of the surface atoms, then friction and wear behavior, corrosion behavior, wettability, these all phenomena they are dependent on the surface energy, and the driving force is nothing but the free energy change associated with lowering of surface energy. So, whenever surface is having, you create the surface, there is a increase in energy, naturally the driving force is nothing but lowering of its energy. So, if you talk about different phenomena that occurs on the surface or that are influenced by the surface energy, these are like droplet dimension. When you go on having a kind of molten metal, and if you just go on pouring it, you will find that it will be poured in a droplet like fashion, or otherwise when you prepare the synthesized powder, you will find that by water atomization or maybe gas atomization technique, you will find that its shape is always spherical in nature, because when it is spherical in shape, it is having very low surface energy because of its very high surface area. So, naturally that one of the important phenomena is that related to surface energy is droplet size, and another phenomena which is very important and it is nothing but the properties of the material, that is wettability, which is again driven by the surface energy. So, you will find that depending on the surface energy your wetting behavior will vary. So, wettability is measured in terms of the contact angle. So, you will find that for example, when the liquid is poured on the surface of the solid, it may spread or otherwise it may retain the dimension of a sphere. So, when contact angle is quite high, you call it as hydrophobic surface. When it is very low, it is called, you call it as that hydrophilic surface, and whole things are driven by the that surface energy or interfacial energy. For example, when you pour a liquid droplet on the surface of the solid, there are three important interfaces which are created. One is liquid to gas interface, one is liquid to solid interface, another one is solid to gas interface. So, if you find that solid to gas interface and solid to liquid interface is higher than that of is lower than that of solid gas to solid interface, you will find that it is hydrophobic in nature. On the other hand, if it is between -1 to 1, it is normal, it is having normal behavior. On the other hand, when the interfacial energy between that when the surface energy between solid to gas minus surface energy between solid to liquid is lower higher than that of the solid to gas, you will find that it is having liquid to gas, you will find that it is behaving in a hydrophilic fashion. So, whenever it behaves in a hydrophilic fashion, you call it as it is highly wettable. So, wettable surface is having certain advantages, especially when you talk about the materials for bioimplant application, it should be highly wettable. When you talk about that self cleaning surface, it has to be wettable. On the other hand, when you talk about that high corrosion resistance coating or that particular material which has to be applied in water environment, very high resistance to the corrosion resistance or erosion resistance, it should be hydrophobic in nature. So, each and every phenomena they are driven by the surface energy. So, you can design the surface based on your requirement when and only when you know the surface energy value properly. Now, there is another important thing which controls the surface energy. So, first important factor which control the surface energy is the area of the surface which is exposed actually. Second important factor which basically controls the surface energy is the environment. Third important factor which controls the surface energy is nothing but the phase along which the surface is created or the surface plane actually. So, if you say the case for typical FCC metals, you will find that it is having the bulk coordination number of 12. So, when you go on creating the surface, you will find that surface energy will depend on at which plane the surface is created. If you create the surface along 100 plane, you will find that the coordination number along 100 plane is 8. So, if you would like to create the surface, you need to break 4 numbers of bond. If you would like to create surface along 110 phase or along 110 plane, your coordination number of each atom at this plane is 7. So, you need to break 5 numbers of bonds. On the other hand, if you would like to create the surface along 111 plane where coordination number is 9, you have to break 3 numbers of bonds. So, you will find that the minimum energy required for creation of surface is along 111 plane. So, if you just categorize the surface energy in ascending order, you will find that FCC 111 plane is having the typical lowest energy than that of FCC 110 or than that of FCC 110. So, you can say that this particular plane is actually most favorable in terms of the minimum free energy. So, you can understand that depending on the plane along which surface is created, the surface energy will vary. So, another phenomena which is usually observed in metallic materials or maybe semiconductor materials, when you see the surface under ultra high vacuum, that is the change in atomic arrangement of the surface. So, there are two important change which are occurred, especially when you just take the pure materials, maybe metallic or non-metallic, and if you see it under ultra high vacuum, you will find that your atomic arrangement on the surface or surface planes is different from that of bulk of the materials. So, the atomic arrangement is very much dependent on the forces acting on it by the other atoms surrounding that particular atom. So, when you talk about the surface atom, naturally you are breaking some of the atoms, naturally some planes are basically missing on the surface. So, if you see the surface atomic arrangement, you will find that the d-spacing of the surface atom and the neighboring atom is a little lower than that of d-spacing of the typical interatomic spacing of the other atoms which are in the bulk. So, this is called relaxation, and another phenomena which is also observed, that is rearrangement of the surface, called reconstruction. So, reconstruction is a phenomena where you will find that there are missing numbers of atoms from the surface, and lattice parameter on the surface is usually higher than that of lattice parameter of the same in the bulk. So, reconstruction and relaxation, these are the two important phenomena which are observed on the surface when you see it under ultra high vacuum. But on the other hand, if you keep it in normal environment, you will find that there is again the phenomena of adsorption from the gas phase, which again lowers the surface energy significantly. So, when adsorption is there, naturally once it is adsorbed, these all molecules in the environment, they are adsorbed, you will not really get any kind of relaxation or reconstruction phenomena, because these are the phenomena which are usually observed on the pure metals and which is under ultra high vacuum, where there is no other impurities in the environment. And if there are impurities in the environment, you will find that impurities, they get adsorbed over the surface, and depending on the kind of adsorption is there, there are different names like Physisorption or Chemisorption phenomena. So, whatever may be both the cases, Physisorption for example is reversible one, Chemisorption is irreversible phenomena, but in both cases you will find that there is lowering of the surface energy to a large extent. So, apart from that, there are few other phenomena which are also observed because of higher energy of the surface. One is segregation phenomena. In alloy system particularly, if you see the surface concentration, atomic surface impurity concentration as compared to that of bulk, you will find that the most of the impure atoms or solute atoms are segregated along the surfaces, as is there in the grain boundaries. So, again the driving force is nothing but lowering of the free energy. You will find lot of clustering phenomena all throughout the surface, where like atoms try to get segregated along the surfaces to minimize its energy. So, now surface energy, so these all phenomena are observed and naturally these all things change the structure of the surface as well as composition to a large extent. So, if you just think of the bulk metallic materials application, whatever things happen on the surface, that might not have significant role, but naturally if you think of applications of smaller structure, particularly for MEMS devices, you will find that this change in atomic arrangement or this change in composition might have significant role on the functional properties of the matter. If you talk about structural properties like coefficient of friction, corrosion resistance, these are also influenced to a large extent by surface energy. For example, if you see the variation of coefficient of friction with surface energy, you will find that higher is the surface energy, the lowering is the coefficient of friction. Because higher is the surface energy, more will be the tendency to reduce its energy when another surface is there on its surface, as a result of which you will find that lesser will be the hindrance towards the motion. So, this is the reason behind the lowering of coefficient of friction with increased surface energy. On the other hand, if you think of the mechanical properties of the material which has also influence on coefficient of friction like hardness value, there you will find that higher is the hardness, naturally higher will be the lower will be the coefficient of friction. because hardness increase whenever there is increased hardness, or maybe the harder the materials are in combinations, or where harder the metal surface is, naturally lower will be reduced will be the coefficient of friction. So, naturally the relationship is very much complex in nature. You cannot say that only surface energy or only mechanical properties which play a role in determining the coefficient of friction, but a kind of combined relationship is there which create role in determining the coefficient of friction. Now, if you talk about the another phenomena which is observed on the surface, that is atomic arrangement of the surface. So, you will find that atomic arrangement of the surface is a little different from that of the bulk. As I mentioned you that depending on the availability of energy, the plane along which surface will be created will depend on. So, usually it is atomically dense plane along which surface is created, because it requires minimum energy to create the surface. Now, if you see the surface atomic arrangement, again this is not ideally smooth in nature. There is always discontinuities in the atomic arrangement of the surface. So, usually if you see the surface atomic arrangement, you will find that there are actually smooth crystallographic planes in a system up to a certain level, and then there is discontinuity. Then again this particular surface continues up to a certain distance, and then again there is discontinuities, one atomic state discontinuities. So, these particularly atomically smooth planes where surface is created is called terrace, and where there is discontinuity by one atomic level, you call it as ledges. And again in the ledge you will find that this is again not continuous in nature. There is actually some of the atoms which are coming out, we call it add atoms, and some space of vacancies are also created over there. Some of the atomic arrangement which are deep inside, you call it kinks. So, kinks, ledges, these are all there along that particular crystallographic plane of the ledge. So, these all phenomena you will observe in the surface if you see under ultra high vacuum. So, this is typical terrace ledge kink model which has been established by 3 scientists, and you will find that in the surface if you see the atomic arrangement, they are really very much free to move. Not only the surface energies are higher, but also you will find that on the surface there are many free atoms, many free vacancies, and creation of vacancies also need much lower energy than creation of vacancies inside the bulk of the materials. So, you will find that it is very easy to create the vacancies, and as a result of which if you talk about the phenomena of diffusion, you will find that diffusivities along the surface is the much higher than that of that gain boundaries and that of bulk of the materials, because it is easy to migrate the atoms on the surface, because it is easy to generate defects on the surface, particularly point defects where atom can get atom can sit and then get diffused in. So, this particular surface arrangement is very important to know, and you will find it if you see it in ultra high vacuum and when surface is highly pure in nature. Now, if you go to a little lower scale, rather if you just go on magnifying further, if you resolve it a little bit to a larger extent, like if you see the microscopic arrangement of the surface, but not really atomic arrangement of the surface, you will find that depending on the zone where you are observing, the structure again varies. It is nothing but a multi-layered structure, where near the surface there are a lot of adsorbed gases and water vapor, or you will find the reconstruction or maybe that relaxation phenomena if you see it under ultra high vacuum. But if you see normal environment, you will find lot of adsorbed gaseous species are there. If you talk about metallic materials which are highly reactive in nature, naturally there is a phenomena of chemical adsorption. So, chemisorption phenomena. So, near to the surface there is always some oxide or compound layer formation, and below that compound layer again you will find very thin amorphous layer which does not have any structure actually. So, it is called bilayer because this particular structural features exactly is vanished on the surface because of the reason that some cold working operation which the surface has undergone prior to its processing actually. So, this bile layer is very important and it is amorphous in nature, and the presence of this layer will be visible if you do OJ electron X-ray photoelectron spectroscopy or OJ electron spectroscopic analysis, or maybe low energy electron diffraction analysis. You will get to know about the amorphousness of this particular feature actually. If you also do the nano hardness analysis, you will find that it is having little bit higher hardness than rest of the material. Below that there is work layer, where you will find lot of dislocations and dislocation and entanglement, and then you will find also the elongation of the grains, which is work layer, and below that there is bulk of the material. So, these all layers are very much important, and if you just see the microstructure of the cross section carefully, you will find that at different scale these different layers will be visible. For example, the layer of the cold worked layer is the thickness varies from 1 to 100 micron, the bile layer to 1 to 100 nanometer, then oxide layer 1 to 100 nanometer, and then the physisorbed layer dimension is very less, it is just on the surface around 1 nanometer. Now, finally, just if you think about different properties which are dependent on surface, they may be categorized into 3 types: physical properties, mechanical properties and chemical properties. Physical properties like roughness and color, they are dependent on the surface. Mechanical properties like micro hardness, rupture strength, fatigue and wear properties, and chemical properties like corrosion and high temperature oxidations, which are dependent on the surface. So, in the next few slides I will discuss about the different physical properties and their role. So, if you talk about roughness is nothing but the deviation of the unevenness of the surface as compared to that of its ideal surface actually, but actually what you see that ideally no surface is roughless actually. So, there is always certain degree of unevenness on the surface. So, this unevenness is created because of, if you talk about the atomic level unevenness, you can understand it from TLK model, where you saw that again in atomically also surfaces are not ideally smooth in nature. So, but on the other hand, if you do different working operation, there are also different kinds of unevenness is introduced on the surface. So, the unevenness on the surface is because of the, or maybe you can say micro scale unevenness on the surface is because of the working operations the surface has faced. The unevenness may be categorized into different terms based on the scale at which you are observing, like surface roughness, surface waviness, lay, surface width cutoff, waviness height. So, these are the different terms which are actually employed to define the surface roughness. So, surface roughness is very fine. When you talk about roughness, it is nothing but it is the degree of unevenness in a very smallest dimension, and usually roughness is measured by contact or non-contact profilometer, and there it is measured in terms of average roughness, that is distance between the top surface and that of bottom, or maybe you can also measure it in terms of the RMS roughness. So, these two terms are used to define the surface roughness, and waviness is nothing but this is again the roughness of the material at a scale larger than the smallest scale. So, this is generated because of the different working operation. So, surface where surface loses its straightness, so you call it waviness. So, waviness width is again a kind of smallest dimension where the waviness is observed, and the dimension of the roughness along which the roughness is generated is called lay, and there may be a lot of flaws on the surface because of different defect generation associated with processing. So, this is very important. So, if you talk about the roughness and its importance, roughness is not really because of the surface energy, but it is the fact and phenomena to some extent associated with surface energy, as you saw in surface atomic arrangement. To some extent it is generated because of the processing operation the surface has undergone, and as a result of which many properties are actually influenced, like luster is influenced by surface roughness, friction coefficient is influenced by surface roughness, wear is influenced by surface roughness, corrosion resistance is influenced by surface roughness. Luster is influenced because higher is the roughness, higher will be the scattering sides, as a result of which surface loses its reflectivity, luster is lost. Coefficient of friction also increases as the roughness is increased, wear value as a result of which increases. Corrosion resistance is influenced because higher is the roughness, more will be the exposed area, and as a result of which naturally corrosion will be higher. So, these are the different properties which are influenced by surface roughness, and this is the slide which shows the different roughness value basically related to different processing operation. So, you can understand that different cutting, casting, processing like melting, casting, different types of roughnesses, different values of roughness is generated. If you talk about investment casting, then roughness level is much lower than that of sand casting. If you talk about different cutting or machining operation, you will find that lapping or polishing induces much lower roughness than that of grinding, and cutting also you will find that by sawing you have very high roughness. On the other hand, by boring, milling, roughness level is reduced. Similarly, flame cutting offers very high roughness, EDM cutting offers quite low roughness. So, different levels of roughness is generated because of different working and processing operation. If you are interested to maintain the roughness to a very low value, you have to choose the processing operation accordingly. So, that another important properties which is influenced or dependent on the surface is the color of the material. So, color depends on that response of the materials towards visible light. So, if you see the metallic materials, they are mostly colorless in nature, because in the metallic materials there is overlapping between valence band and conduction band. So, electrons which are basically absorbs most of the energies associated with the typical visible light, they all reflects it back, and as a result of which there is not very less amount of energy is absorbed, and all the energies associated with the different wavelengths of visible light, they are basically reflected back, as a result of which you will find colorless in nature. On the other hand, some of the metallic materials like gold and copper, they are having large numbers of electrons in the d bands. So, d levels electrons are there. So, as a result of which basically when the visible light is exposed onto the surface, they basically they are the different atoms, different electrons absorbs different types of different levels of energies, and as a result of which you will find that when they reflect, maximum energies which are emitted, depending on that the color varies actually. So, you will find that golds are mostly yellowish in nature, which is having the wavelength in the range of 7000 to, which is having wavelength in the range of 6000 to 6500 angstrom nanometer. On the other hand, you will find that if you talk about the silver and then iron, they basically reflects most of the electrons, I mean most of the energies. So, they are basically whitish in nature. So, depending on the electronic configuration, you will find that the energy will change. So, this particular thing again is dependent on the surface, because surface is exposed to the visible light, and you will find that if you are interested to colorize the surface, you have to form the compound layer on the surface of the metal by exposing it to different environment, and there are different ways by which you do that. So, we will discuss about these different techniques when we discuss about the conversion coating, chemical as well as electrochemical conversion coating. Then if you talk about mechanical properties, hardness is one of the important mechanical properties which comes into picture. So, it is nothing but it is the measure of its resistance to plastic deformation. So, basically it is measured by indenting it with a indenter and subsequently measuring the size and shape of the indentation mark, and there are different scales by which hardness is actually represented, like Vickers scale, Knoop scales, Brinell and Rockwell scale. It is dependent on there is also small scale of hardness measurement, which is nothing but the ordinal scale, where the relative scratchability of different minerals are basically sequentially placed, and Mohs scale level 10 means it is the diamond highest hardness, and level 1 is talc which is having lowest hardness. But this is, as I mentioned you, this is the ordinal scale. So, you cannot really say which one is having how many times higher hardness than that of the below one. So, like diamond to corundum, if you see the hardness of diamond, it is 4 times that of corundum. On the other hand, if you talk about the corundum and topaz, it is again 2 times that of hardness of topaz. So, it is really relative scale, and like that there are several other small scale of several different minerals as well. This is the earliest way of representing hardness, but now there are different scales or different ways by which you measure hardness. It is very much dependent on the microstructure and composition of the different materials actually. So, if you talk about the iron and steel, it is having hardness varying from, for example, 100 VHN or hardness 100 Hb to 700 Hb, and it is if it is copper and its alloys, it is having quite low hardness. So, if it is aluminum and its alloy, it is having even much lower hardness. So, usually pure metal is having lower hardness, and you can harden it by different hardening operation like strain hardening, grain refinement, induction strain hardening, then grain refinement, precipitation hardening, edge hardening. By different operations you can increase the hardness to a large extent. So, hardness is again a kind of primary mechanical properties which influences many important surface dependent mechanical properties like friction and wear, corrosion property, and it is dependent on the microstructure and composition of the materials, and it is also dependent on the surface structure, because if you do any kind of operation on the surface, the hardness will also vary, particularly the scale of hardness will vary. So, if you measure the hardness in nanoscale with the help of nano indentation technique, you will find that the hardness of the surface is much higher than that of hardness of the bulk of the material, because of the presence of work hardened layer or oxide layer or the bile layer. But on the other hand, if you measure it on in micro scale and also in macro scale, you will find that effect of surface natural atomic arrangement or natural change in structure because of the surface energy is not visible in the hardness value. You will get the informations about the bulk hardness of the material, which depends on the microstructure and composition of the material itself. Flexural strength is another important mechanical property which is dependent on the surface, which is nothing but gives you information about the failure in bending. So, this is dependent on the surface because often failure starts from the surface flaws, surface impurities where stress concentration is much higher. So, it is also taken as the property which is dependent on the surface. So, if you just improve the surface finishing, or maybe if you increase the surface hardness to a little extent, you can increase the flexural strength to a large extent. So, in this particular talk we discussed about the importance of the surface, then surface energy, the phenomena related to surface energy and the properties influenced by the surface energies. We also discussed about surface dependent physical properties and primary mechanical properties like flexural strength and also hardness, and other important mechanical properties which are dependent on the surface like the wear resistance and also fatigue property, that will be discussed in the next few classes, and surface dependent chemical properties like corrosion and high temperature oxidation will also be discussed in the next 2 classes. Thank you very much.